Welcome to another installment of Human Anatomy and Physiology 2. Today's subject is going to be the lower respiratory system. In our previous meeting, we talked about the structures of the upper respiratory system, which we got down as far as the larynx, which represents a boundary between upper and lower respiratory systems. The lower respiratory system, like the nasal cavity and sinuses, has a pseudostratified columnar epithelium with cilia that can sweep a layer of mucus and any trapped dust and debris and bacteria up out of the lungs, and then that can be swallowed down to be destroyed in the stomach. The conducting zone in the lungs represents airways, pipes that can carry the air down to the respiratory zone where the actual gas exchange will happen. So the trachea and bronchi have C-rings of hyaline cartilage in the walls. We call them C-rings because they're not continuous circular arrangements of cartilage. They're just partial rings of cartilage so that the airways can be narrowed or expanded, and also the esophagus can expand during swallowing. So here's a little kind of a rough cartoon of the C-ring of cartilage and part of the trachea, and you can see that there's smooth muscle that occupies the remaining parts of this, what would be a circle, so that if we can contract that smooth muscle, we'll have bronchoconstriction, or dilate it to have bronchodilation. Bronchoconstriction serves at least one purpose, which is to increase the velocity of air during sneezing and coughing to help produce the kind of shear forces necessary to clear any debris or obstructions out of the airways. You can see the esophagus here. During swallowing, a bulge will travel down the esophagus by peristaltic contraction, and we need to have some way for that to pass by the esophagus, and that smooth muscle wall can deflect or deform. And here's a little micrograph of the wall of the trachea, part of the wall of the trachea. We can see the classic look of hyaline cartilage, the chondrocytes in their lacuna. We can see the ciliated pseudostratified columnar epithelium, again normally covered by a layer of mucus, which can then be swept out of the lungs. The trachea branches to form two primary bronchi, the right and left bronchi. The right one's a little bit larger in diameter and a little more vertical in arrangement, and just for interest's sake, it's the place where objects are most likely, foreign objects that manage to get past the larynx in small children are more likely to be trapped in the right bronchus and will have to be removed by endoscopy. And then there's around 23 branches. The bronchi keep branching and branching into smaller and smaller tubes, and then eventually we reach the respiratory zone. Bronchioles are the smallest of the bronchi, and they are less than 1 millimeter by definition in diameter, and they have only smooth muscle in their walls. There's no longer any cartilage in those small vessels, and if they bronchoconstrict, they may actually completely prevent the movement of air, or they may just hinder airflow during an asthma attack, for example. And here's a little cartoon illustrating the branching effect. 23, imagine 23 branches of these bronchi into bronchioles before we get to the respiratory zone of the lungs. You can notice also in this diagram that the lungs have multiple lobes, so that the lungs aren't one contiguous mass of bronchi and alveoli. There's different lobes which are separated by connective tissue boundaries, so that perhaps if some ailment arises in one lobe of the lung, and in fact the lobes are divided up into segments, in one segment of the lung it will be essentially isolated there for a time because of the connective tissue barriers. So one bronchus, if I get a hold of one of these, would give rise to branches that will form a segment of the lung. This branching bronchus would also then give rise to another segment of the lung. So some divisions of the lungs. Eventually, we reach a smallest bronchiole. The terminal bronchioles are the last bronchial branch before we get to the respiratory zone where the actual alveoli are located. Those are the air sacs where gas exchange diffusion happens. And then this bronchus right here, this bronchiole I should say, is called a respiratory bronchiole because it actually has some alveoli, air sacs, budding right off from its surface. So now it's called a respiratory bronchiole. And then we have acini of alveoli clustered on the ends of these respiratory bronchioles. The walls of those alveoli are made up of simple squamous epithelial cells. So it's basically a single cell thick sac, very, very thin, so that oxygen can diffuse very quickly into the blood. But there's also elastic fibers, elastin protein in the walls of these alveoli. So if you stretch them, when you inflate them with air, it's much like blowing up a balloon. They have elastic tension, and they will recoil if allowed to, and reduce their diameter just spontaneously. So we have stretch and recoil happening of the alveoli every time you breathe in and out. There's also a lot of blood capillaries in the walls of the alveoli. Here's a cartoon showing that each alveolus is kind of crisscrossed on the surface by blood capillaries, so that we have lots and lots of surface area of the relationship between the alveolar wall and the capillary wall, and then the red blood cells within those capillaries, so that we can efficiently diffuse some oxygen into the blood. So here comes the pulmonary artery, some arteries branch and branch, giving rise to these capillaries, and then we'll coalesce all those capillaries into pulmonary veins, and then finally the pulmonary vein will carry blood back to the heart. Here's just fun to look at an electron micrograph of the respiratory zone of the lungs. Here you can see an alveolar duct and parts of different alveoli that have been cut through as this tissue is sectioned. And little A's represent alveoli. You can see how thin the walls of the alveoli are. So that's a single cell thick wall of epithelial cells of the alveolus, and then all these wrinkles are actually blood capillaries in the surface of the wall, so that just amazingly thin simple squamous cells make up both the alveolar wall and the capillary endothelium. Pretty cool. So here's a cartoon so we can kind of differentiate a few things that I want to mention real quick. The alveoli, again, are constructed of these little cobblestone-looking guys. Those are simple squamous alveolar epithelial cells called type 1 cells. So that's what we call the structural cells. In the walls, or attached to the walls, are blood capillaries made up of endothelial cells, simple squamous endothelial cells here. And the oxygen has to diffuse through those type 1 alveolar cells through the basement membrane of that epithelium, the basement membrane of the endothelial cells, and then right into the capillary and into the red blood cells. So that collection of structures is called the respiratory membrane. That's what the gases have to cross over to go from the air in the alveolus into the capillary blood, or from the capillary blood, in the case of carbon dioxide, into the alveolus to be breathed out. The respiratory membrane is a really important structure of all land organisms that use oxygen, and that are, well, I should say animals. There's also another type of cell called a type 2 alveolar cell. These green ones, they've drawn them, are called type 2 cells. They secrete a detergent-like molecule that dissolves in the water of the surface of the alveolus. The cells are wet or moist. They're covered by a thin film of water, and that water has in it some surfactant, it's called, which we'll see later how that helps us with ventilation or breathing. And then finally we have some alveolar macrophages, which are free to roam around in the alveolus and phagocytize any debris or bacteria that do, in rare circumstances, make it all the way down into an alveolus. Usually any debris or dust or bacteria that enter our oral cavity, or nasal cavity I should say, during ventilation stick to the mucus somewhere along the way and don't make it this far down into the respiratory tract. And here again is a nice electron micrograph, once again to show us just a small part of the wall of two alveoli and some of the blood capillaries you can see. One of the reasons I put this micrograph in is so you can see how tightly packed the red blood cells are as they transit these capillaries. They're not floating down the lazy river, as I like to call it, with reference to water parks. The red blood cells are intentionally packed right up against the surface of the capillary so that oxygen has the minimum possible distance to diffuse from the air in the alveolus through all those respiratory membrane structures right into the red blood cell and onto the hemoglobin. And consequently, it's very efficient. This diagram reminds us that the lungs occupy the pleural cavities. And the pleural cavities are lined with the parietal pleura, a serous membrane, an epithelium that produces a small amount of lubricant fluid, and then there's another identical membrane attached to the surface of the lungs called the visceral pleura, and those two pleural membranes can glide effortlessly or frictionlessly on one another as we expand and contract the lungs. There's no loss of energy and friction, no scuffing happening in here under ideal conditions. Also, the heart we can see in the pericardial cavity wrapped up by that double layer of pericardial serous membranes. So again, the lungs are divided up into 3 lobes in the right lung, 2 lobes in the left lung, and then each lobe is divided up into about 10 segments. And again, those are separate little subdivisions separated by some connective tissue between the different segments. This diagram is a good one to be thinking about the relationship between the lungs, which are elastic and have recoil and tend to want to shrink and contract. They're like half blown up balloons, each one of the alveoli, and therefore the lungs. There's a tremendous amount of energy stored in that elastic protein that wants to pull those lungs down inward. But they can't, because the lungs are in the pleural cavity, sealed up in such a way that the chest wall is another elastic structure comprising the ribs, the intercostal cartilages, the costal cartilages, I should say, the intercostal muscles, and that box of tissue is elastic. And you might want to think about it as though if we took the chest, the thorax, as a brand new construction project with nothing inside of it, and then inserted the lungs into it, partly inflated like they are, sealed everything up, and watch what would happen. They would recoil and pull the walls of the thorax inward a bit, and the more you pull them in, the more you stretch them out of their relaxed position, and the more they are resisting that movement. So the chest wall is pulling outward. So when you're resting, let's say you expired some air at rest sitting there, and then no more air was moving, but you kept your glottis open. During that moment, there would be tension, the lungs pulling inward, and the chest wall, the elastic chest wall, pulling outward. So we'll take a look at the consequences of that, but I thought this would be a good diagram because you can actually see some kind of tissue structure there to give you a sense of there's some real material there that will have an effect. Here's a picture actually of a cadaver lung that's been perfused with some latex, some colored latex, so that we can see the pulmonary artery and its relative position to the primary bronchus and the pulmonary veins that are at the hilus of the lung. And just for interest's sake, and then so we're looking at the medial surface of the lung there in this drawing, in this picture. Here's an interesting thing. Each lung has 2 blood supplies, 2 sets of arteries and veins that bring blood to the lungs and carry blood back from the lungs. One set is comprises the pulmonary circulation, and that's the circulation of the lungs we've been talking about ever since chapter 19 when we talked about the cardiovascular system. So there's all of the cardiac output, 5 liters per minute at rest, is going through the pulmonary artery to the lungs to be oxygenated and then back to the heart through the pulmonary veins. But that air isn't a good source of oxygen for all the tissues of the lungs because it's coming from the capillary beds of the body and it's already been somewhat depleted of oxygen. We need to feed the tissues of the lungs with something a little bit better than that. So there's another circulation, arteries that come from the aorta, high pressure blood, 120 millimeters of mercury systolic pressure, full of oxygen, saturated with oxygen coming to the lung tissues. So a large volume of low pressure blood, the right side of the heart, there may be 18 millimeters of mercury pressure during systole of the right heart. Here we have 120 millimeters of mercury systolic pressure. So large volume, low pressure for the pulmonary circuit, a small volume of blood at high pressure going through the bronchial circulation. I have mentioned a number of times in chapter 16, chapter 19, and possibly others that there is an enzyme in the endothelium of the lungs, other organs too, but especially in the lungs, that contains angiotensin converting enzyme. So when renin is released from the kidneys and initiates the production of angiotensin to angiotensin, then angiotensin in the circulation is spontaneously converted to angiotensin II in the lungs. I drew this cartoon, I embellished this cartoon to illustrate the two circulations of the lungs. The pulmonary artery carrying 5 liters per minute at rest to the lungs to be oxygenated pulmonary veins. And then all that blood from the pulmonary veins, this goes from the left ventricle out to the systemic circulation. There's a small amount of blood that travels through the bronchial circulation arising from the aorta to an artery that then feeds all the tissues of the lungs, all the bronchi and bronchioles and smooth muscle cells and alveoli. And then once the blood goes through the capillary beds of those capillary beds, the blood returns then to the circulation. And here's an interesting point of trivia. You'll love this. You might imagine that blood from the aorta traveling through some capillary beds, then we call it venous blood after that, would return to the right heart so that it can join in with all the blood coming from the inferior and superior vena cava to be reoxygenated, but it doesn't. It joins in with the blood of the pulmonary vein, the oxygenated blood. So we have some already depleted blood mixing in with the rich oxygenated blood from the lungs as it enters the left atrium. So technically, the saturation of hemoglobin in the systemic arteries can never be 100% because we're adding some blood, mixing in some blood that has already been extracted of some oxygen by tissues of the lungs. Another interesting point of trivia, not only is there no way to have 100% saturated blood in the systemic arteries, I've asked you in the past the question, which ventricle has the higher cardiac output? And I wanted you to answer neither, because if that were the case, one would be ahead of the other and blood would accumulate at the doorway of the less active ventricle. Well, so we said no, there's neither, but actually technically the left ventricle pumps more blood because we have this extra bit of blood going in this loop from the aorta to the lungs and right back again, and that's blood that never actually comes to the right heart. So the left ventricle does in fact have a larger cardiac output, very small increase but larger cardiac output, just for fun. Okay, what about the gases? Piled upon us right now, is a couple of miles deep pile of air molecules, and air molecules have mass. They're little tiny massive particles moving around at tremendous velocities, crashing into everything in sight, but this big pile of air molecules produces a lot of pressure. The collisions of all those massive air molecules with every surface creates pressure. Pressure, as you know, is force per unit area, and in this case imposed by those massive particles colliding with various surfaces. So there's 760 millimeters of mercury pressure of air stacked up on top of us right now. The respiratory system operates, inspires and expires air by making very small changes in the pressure, in the air pressure inside the lungs, of actually only about 1 or 2 millimeters of mercury, probably typically at rest. And so very small changes in pressure, and we want to talk about those changes in pressure, and instead of saying 761 or 759 to talk about the differences, we just call atmospheric pressure 0, and then if the pressure goes down from there in the lungs, we call it negative pressure, and if it rises, positive pressure, and then we just talk about the differences. So we might say that the pressure in the lungs changes, goes from 0 to 1 or 2, and then from 0 to -1 or -2 as we move air in and out. So what do? For inspiring air, we increase the volume of the lungs, and that causes the pressure to drop by a couple of millimeters of mercury at the most, and then air moves from the atmosphere at higher pressure into the lungs at lower pressure. So air flows from higher to lower pressure, just like blood flows from higher to lower pressure. And then when we want to expire some air, we decrease the volume in the lungs, and that causes the pressure to rise 1 or 2 millimeters of mercury, and air just flows out from higher pressure inside the lungs to lower pressure outside. Incidentally, as I mentioned before, if you just kind of stop moving in a relaxed way with your glottis open, all the pressures will be identical. There will be atmospheric pressure outside, atmospheric pressure inside, and no airflow. There's another consideration to be made with respect to pressure in the thorax and this system, and that is intrapleural pressure. There's a different pressure between the pleural membranes because we have two opposing forces tugging on those pleural membranes, the lungs pulling inward, the chest wall pulling outward, and so there's this tension there. And so if we stuck a manometer in between the two, we would read a negative pressure, a lower pressure, inside that intrapleural space. Nothing can get in there so that nothing happens. There's no movement of air or water into that space. There's no access, but there's a low pressure in there, a negative pressure in there. So intrapleural pressure is always lower than atmospheric pressure, lower than the pressure inside the lungs. The pressure inside the lungs, the alveoli and so forth, is called the intrapulmonary pressure. Pulmonary just means of the lungs. So intrapulmonary pressure is the pressure inside, and the intrapleural pressure is always lower than the intrapulmonary pressure and lower than atmospheric pressure. Any fluid that accumulates, the serous fluid being produced by the pleural membranes, is scavenged up by the lymphatic system and returned to the venous blood so that no fluid accumulates, except in pathologic conditions. You could have a fluid accumulating in there. It's called a perfusion, an effusion, I should say, not a perfusion. Fluid escaping from the vascular system and winding up in the intrapleural space. But normally there's no fluid in there and there's just this tension in there. Well, there's an interesting consequence of that tension. So here's a little diagram showing the lungs pulling inward by elastic recoil, the chest wall, the elastic chest wall that's been being tugged on, pulling outward, resisting that compression, that shrinking. And if we introduce a pathway, if we damage the parietal pleura and let some air enter, or if we damage the visceral pleura and let some air out of the intrapulmonary structures, then air can get into the intrapleural space and the lung will collapse. So if we have an injury, I drew a lightning bolt, probably not very real world, but we didn't want to get too macabre and draw a knife or something there. So anyway, if there was a trauma in which we damaged the parietal pleura, air could enter and the lung would collapse. Or if there was a tear in the lung, an injury to the lungs, some people are prone to injuries to the lungs during very, very vigorous exercise. There could be an opening through which air could go from the intrapulmonary space out into the intrapleural space, and the lung would collapse. That is called atelectasis, lung collapse. Atelectasis can refer to just individual alveoli collapsing, but it's often used to talk about a lung collapse or part of a segment of the lung. If a bronchiole gets plugged, that will lead to collapse of the alveoli that are downstream of that bronchiole. If it's air that comes into the lung through an opening in the pleural membranes and we have lung collapse, that's called pneumothorax, because there's air. We of course have air in the lungs all the time, but there's now air in the thorax where it shouldn't be. And so that's the reference in that terminology. So next time we'll start talking about the actual mechanics of ventilation. How do we get air in and out of the lungs? And then we're going to start talking about the properties of the air that's in the lungs and the pressures and how we can get oxygen from the alveoli efficiently across the respiratory membrane into the capillaries, and then from the capillaries in the body tissues to diffuse away into the cells where it's needed. So join me next time for another discussion about pulmonary physiology.